So let's start with the RISC-V introduction, but I take it a little bit from say, presenting myself. As I said, I'm in a prototype lab. And I want to introduce the first concept of today, the technological readiness level, okay? You will see why we need this concept. So I come from the Barcelona Supercomputing Center. It's a center in Spain. We do operate a supercomputer that is Mare Nostrum 4, beautiful, installed in a chapel. How many of you have been visiting? I know at least 2 that have been visiting. Good, nice. So how many from BSc we do have? I see, yeah, 1, 2, 3. They are in the back of the room, okay. So we have a supercomputer. We have 4 departments for doing research, okay, that are computer science, life science, earth science, and engineering. And then we are, say, an education institution. We are connected to the university, so we have a master's student, the undergrads, and PhD students, okay? So you can remember these 3 things. Here are the institutions that are, say, supporting us, funding us. This is our computer. So I'm zooming in very, very quickly, okay? So BSc, 4 research departments. So I'm not operating this machine, I'm doing research. In these 4 departments, I'm working here, computer science. What do we do here? The idea is that we contribute, we influence the way in which the machines are built, programmed, and used by users, okay? That's the idea. So if I talk about co-design, there's a bad word, I should not say it, okay? But co-design in our world is being able to understand the problems so that we can report that to different communities. The community of the hardware guys that are making the hardware, the community that are operating the machine, making the system software, the compiler, and so on, and the scientists, the users, okay? Zooming in a little bit more, I arrived to the mobile and embedded based HPC lab, where I come from. That's my team, where we do research every day. Okay, and here I have a timeline that shows how old I am. We saw in high-performance computing in the beginning of the 90s is not precise on purpose, okay? This is a little bit a story that, so in high-performance computing, we started using commercial CPUs in the 90s, right? Before that, there was basically special machines that were built by governments just to do mostly, let's say governmental task, okay? And I don't want to say if it is military or not. So in the 90s, we start having this idea of this crazy guy, Bill Gates and so on, that he wanted to have a PC in every house, right? So that opens a market, a huge market, and in the market we start seeing a lot of well, mostly Intel, but a lot of CPUs. A lot of goods on the market make the price lowering. So the price is low, the technology is good. Here enters the high-performance computing people that are usually parasite of the market. So whenever you have something that is doing good computation and is cheaper because it's pushed by the market, in HPC we usually take it and you use it in the data center. Okay, that's always the story. And this happened in the 90s with the CPUs, and it happened again at the beginning of the 2000s with the GPUs. Okay, so we had a lot of gamers, a lot of market with the graphic processing unit, and that was in the end just floating point capability under our desk. So this has been used and put in the data center, and it happened again around 2010 with the mobile technology, okay? That's the first concept that I wanted to tell you today. In high-performance computing, nowadays is pretty difficult that you have something that comes to high-performance computing and then go back to the commodity market. It's probably the other way around most of the time. Sorry, no, I went back. Okay, now I wanted to introduce, so how many of you are familiar with the TRL concept? Okay. So, okay, this is important because I think it gives you the level of maturity of the technology in which you are working on, okay? So, as I said at the beginning, in BSc, we do have the supercomputing, the Mare Nostrum supercomputer. That's a very high TRL. So TRL is a scale that say, historically has been defined by NASA, okay, for making things flying, basically. So you start from being a paper airplane. So the lower level are basically ideas that you discuss, that you start quantifying, and going higher in the number makes these ideas more and more concrete, more and more viable, in the sense of, in the original idea of NASA, more and more safe to flight, okay? And then the highest values means that you have a product, something that you can provide to a community, that you can offer a service, that you can offer some support, and so on, okay? So now let's move these to the computing things. So the first things probably here below are the things that we can discuss on a blackboard, architecture, this kind of, so algorithm, okay? And going higher and higher, we have systems that are more and more mature, that can be given to scientists that are not familiar with the low level of computer science or architecture. Now, I would say that Mare Nostrum, the beautiful picture that I showed you before, is here, okay? What we do in our lab, and I have, my idea was to introduce this at the beginning, but the last slide will be a picture of what we have in our lab, so that you can map it, and actually you can tell me which TRL you would assign to the system. So in our lab, we are moving definitely not in this system. We use commodity stuff, okay? So we buy things from the market, but we assemble it together to do prototypes, okay? So it's definitely not here, it's somewhere here in the middle. And this is, I think, the first excitement of today. I mean, what I really like of my job is that I can touch things that are here. In not all the jobs you can do that, okay? If you're giving support in a data center, you stay here, right? And if you just do theory, sometimes you just sit here, right? I really like the fact that I can sit here in the middle, and I can influence the idea below here, and also, well, I like to think that at some point our test can also influence the product up here, okay? We started this years ago with the ARM technology. ARM, how many of you know? Okay, ARM is basically everything that powers our mobile, but also probably your washing machine, your smart bulb in the house, domotics, and everything, almost everything is ARM technology there. So in the lab, we had these ARM systems, and now we are transitioning to RISC-V based system. We have a little bit of both. As I said, with, say, low technology, well, middle, so not really low, because the chip most of the time is already there. Okay, so, well, here you have the link. Is definitely not visible, but you can visit the web of our team, but probably it's better if you talk with me since I'm here. So the first concept is the TRL. Here you see the first nerdy happy face. Here, yes, I'm promoting myself because these are two works that we did in the past for evaluating the ARM systems. Definitely not something that is needed for this course. Just if you want to go deeper in this sense, here you can see two works. This afternoon, when you are in the spa, you have very refreshing reading. Okay, so here you have the picture of some of our systems, the ARM-based systems and the RISC-V-based system. How many of you are familiar with this HiPEAC unmatched? How many of you knows what it is? This is Okay, so we have people that really touches RISC-V firsthand. Good. And this is a slide that I wanted to, so you had to have it, so because it's something that I really attach to. It's not only research, it's not only, say, engineering, it's not only science in the sense of doing research and having contact with companies, but it also has to do with education. Usually what we do in our lab, we usually use it also for this student cluster competition. How many of you knows, or how many of you were in the student? Nobody. Okay, that's so. This is a competition that happens every year, 3 times a year, in the Asian Supercomputing Conference, in the ISC, that is the European Supercomputing Conference, and the HC, in the Supercomputing Conference in the United States. So every year you have 3 of these competition, and you have teams from all over the world that can take their own cluster, and the organizer propose challenges to be solved. So they usually propose challenges in advance, and the only limitation you have is that you have a power cap. So you cannot pass 3 kilowatts until this year. Starting from this year, they pass it to 6 kilowatts. That's pretty strange because we have energy crisis, but they increase the power cap. That's not nice, but in reality there is a reason. Later, if you want, we can discuss about this. Oh yes, please.
What's the competition called?
Student cluster competition, SCC. Yeah, it's pretty. You see, it's definitely not smart from my point of view of not putting the name in the slide. Thank you. I will fix it. Going back to a competition, you have a power cap, and basically you prepare from in our case, we go to the European one. We prepare from November until May, and then you go to the conference, you bring your cluster, and you show on the show floor, at the exhibition floor, for 3 days. You have different challenges, and you submit your result and so on. We never won any performance prize. We won quite a few fan favorite awards, because so basically the award that proved that we are nice. But what we really like to push is our name and the concept that is behind our name, not only flops. We always went there with some architecture that was different. With some ARM cluster, last year we went with a RISC-V cluster, and it was really exciting and a really nice educational experience for the students, okay? So in whichever level you are, even if you are a master student, you can still participate. If you are a PhD or higher in your studies, in your evolution, you can participate as advisor or just be aware that this is there. But I think it has a strong link with what I'm going to present today, and that's the reason because I wanted to show you. Okay, so BSc, Computer Science Department, we do research how to operate and get machines better. In that world, we do have a lab in which we have prototypes with mid-TRL, and we also do some education. That's the end of, say, my introduction, to introduce myself and the concept we need to now look at RISC-V. Are we fine? Questions? If we want to talk about the BSc, of course, offline, we can. So I'm more than available. What is RISC-V? Okay, so I mean, this is something that you can take a YouTube video and look at it, okay? So, and I'm sure that even the people that are in the room that were shy before can get it pretty quickly. It's an instruction set architecture, okay? That is royalty-free, is open source. Be aware that I'm saying instruction set architecture. It's not a CPU that is open source, okay? So it's defined as a very simple instruction set architecture. In fact, in this, but you cannot read it. It was not on purpose that you. I didn't want that you were able to read it, but I just wanted to put it because here you have basically the full instruction set in this page, okay? So it's pretty new. It has been ratified in 2014. by the University of Berkeley. And yeah, okay, it's called RISC-V, and 5 is because it's the 5th attempt, the 5th generation by Berkeley in doing this instruction set. So in the university they did have previous versions. This is the one that has been really pushed out and has been, well, is being promoted, I would say, these years, nowadays. Here you have links. I think most of them are in the Google Classroom. There is a book and a couple of books and so on. So a set of instructions that everybody can take and make a CPU out of that without paying anybody. Okay? This is the concept that you have to take away. This is important because we will see soon that is definitely not common in the market, this kind of, so usually if you want to do your own CPU, you have to pay somebody. Either you have to buy the CPU or you have to pay some royalties for using the instruction that has been created by some company, okay? Now, a big value of using RISC-V is that the hope is that it can set a standard. Setting a standard, I think I can here start defining what's a standard, but how we define it. I just want to give you an example. So I don't know if you are old enough to go around with these kind of things in your pocket, right? When we had the mobile phones with different plugs, and now we have the laptops with different plugs, okay? So the value of the standard in this world is when all the companies that are making profits, okay, so their life is to make money, okay, they just agree on a standard and say, okay, let's use USB in this case, okay, universal serial bus, so that everybody can use the same plug unless you use Apple. So if you use Apple, I'm sorry, I mean, it's not your class, okay, today. But that's the idea of, so having a standard means that there is a concept that goes beyond your profit, okay, that sets a standard for everybody. And you can build, everybody can build on top of that to do their profits, okay? So it does not have to do with profit. The profit can come later. So that's the very first concept that needs to be taken into account now, okay? Now let's see more familiar, so other example of having standards. So in networking, you know about Ethernet, so we have a standard, and you can have implementation that are, say, open source and closed source. So here, this is the column of the open source implementation, a column of the closed source. So in the operating system, you have this POSIX standard, you have Linux, that is the open source incarnation of the standards, and Windows, right? In the database, we have SQL, and then you have the incarnation, the MySQL is the open one, Oracle has the closed one, okay? I'm just giving you example if you are in this world that this idea is not new at all. So actually the technology world is built on top of that, right? We define a standard and then we build on top of that. Well, for the instruction set architecture, we don't have that, okay? So there is no standard on top of which we can build. Okay, and here you probably understand where I'm going, right? So we are suggesting that RISC-V can really set that standard. And I want to give you a short history of the ISA, why we don't have that standard, okay? So Intel uses today what we call x86-64, that is probably what you have in all your laptops, unless you use Apple. Anyhow, but this is sort of acquired standard. It wasn't supposed to be a standard. It's just the market that promoted it as a standard. So it's just the most common product that is in the market. Then SPARC. I don't know if you heard about SPARC. SPARC has developed in the 80s. It became, it was sort of shared things between companies. it was the architecture of one of the most powerful supercomputing, the K computer, the Japanese. So it was around, probably you are old enough to hear, to know about the K computer. But then in 2017, basically fade out and is not there anymore. MIPS, how many of you knows about MIPS? This was, okay, because you studied on a Patterson book, right? Okay, right, okay, good. And actually it's pretty similar to RISC-V. It's not, I mean, it's not so different. But the company itself has been sold. So the company that defined the instruction set has been sold at some point in 2000, I don't remember. It was around when I moved, actually it was funny because when I moved to Barcelona Supercomputing Center, I was, at the same week, I had the contract with Imagination Technologies to develop things on MIPS in the UK, and I decided to go to BSc to continue doing, try to continue doing research instead of jumping to a company. And 4 years later, 5 years later, yeah, around 2019, I remember that we were hiring because there was a new project starting, and there were a lot of people coming from the UK because Imagination Technology was basically shutting down the MIPS project. So I was seeing myself 4 years later going back to looking for a job at BSc. But in reality, I probably did the good choice in that in 2013. Anyhow, beyond my experience, the funny story is that if you look now what the MIPS is doing, they are doing RISC-V. So here I leave you yeah, this is a technological gossip. It's not really something that add information. Then the IBM Power. IBM Power is another closed source instruction set that at some point IBM came and say, let's open it. And everybody should use it. It's a standard. IBM is a very powerful company in high performance computing, blah, blah, blah. They are very, and they open it, but nobody took it. So nobody, because say the structure and the way in which they oblige you when you use it, it was not well accepted by the market. So you start seeing that it's not fully 100% technical here. There are market things. And then there is ARM. ARM is this great, it's really a huge market. The instruction set is beautiful, it's small, you can operate a washing machine and a supercomputer, and it is a company that was based in the UK, so it was European, so also for a European project was great. So we started in 2013 pushing for ARM and okay, yeah, let's do the European high performance computing network, blah, 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 blah. But then at some point, ARM has been sold to a Japanese company. So everything that you build basically in just 2 days changed of a flag. And it's not European anymore, but the headquarters is still in UK. And then you have Brexit, and then it's impossible. So you cannot control that kind of things, okay? So we need a standard to just be, try to be as independent as possible from these kind of dynamics that are, say, human or market dynamics. Okay, so here you have all the philosophical questions that I try to address with all this story. If you have to start tomorrow with your beautiful software project of your life, what architecture would you use? So if you have to develop tomorrow your smart washing machine, what CPU would you put, right? Maybe in the washing machine you don't have to put much of a software stack. It's not a good idea, but a good example. But you understand me, right? So if you have to choose a technology and build on top of that, you have to go through these risks, right? And so the idea is that RISC-V can be an answer to this. Another problem that we have today, maybe you're not familiar much with this, but so how many of you are working with IoT and embedded devices? And there are people, yeah, yesterday was in a dinner with one of you that probably is in the room, and he was saying that he was using system on chips, right? System on chips are basically a collection of different, say, IPs, intellectual properties, that are doing things, right? You have the GPU, the CPU, I don't know, camera, handling for sensors, these kind of things. And so if probably you know the Nintendo Switch, right? The Nintendo Switch has a system on chip on it that is a collection of several IPs. And all these IPs are usually suffering this kind of things, right? Because every provider needs to take an instruction set and build the software stack on top of this. So you can have in the same system on chip, you can have different players that are different providers they need to develop their software based on the instruction set of their IP. And then we put it all together and we buy it. Right? And when we have to use that system on chip, we have, if I'm using the GPU, I have to use this software stack. If I'm using the CPU, this software stack. Sometimes both are ARMs, but they are not the same ARM. So one is 32-bit, the other is crazy, right? So this is fragmentation of the system on chip. So SoC is system on chip. So we have this phenomena, right? Maybe you are not exposed to this because you are studying and you are not building systems, but this is happening underneath the things that we are using every day. Okay, so why this happens? Usually it happens for 3 reasons. The first one is that the ISA that we have today in the market are too big or too complex to be implemented in some context. If you want to do a washing machine, maybe you don't want the x86 complexity of the instruction set with 1,000 pages. No, you want something simpler. And then we have that often the SoC provider buys IP from third parties. So they are not really, so I can provide an IP, but I'm not the owner of the technology that I'm providing. The typical thing is that I am building a sensor reading with ARM architecture, okay? So I'm not the owner of the instruction set. I'm the expert in the sensor, not in the... And the third point that, yes, I can educate you on this, don't do your own instruction set to save money, okay? This is a bad idea because it's the typical thing that I say, oh yeah, I put together 10 instructions, nobody will care about it, but always if you integrate your project into something else, this will be something that will limit the rest of the world. That's a bad idea. Try to use a standard before inventing your own things. Okay, I'm not, at least in this context. I don't want to kill your imagination and your creativity. Okay, so here the business model. If you go with Intel, you basically what Intel does. They develop their own architecture. They have their own ISA. They implement it. And they sell you a chip, okay? So that's it. You cannot influence that chain of choices. With ARM, is a little bit more flexible. ARM offers 2 products. The first product is the ISA. You can buy the ISA, well, actually you can rent the ISA, okay? So you contact ARM, they give you the book with all the instructions, and you pay a lot of money. And starting from there, you can build your own chips based on the ARM instruction set. This is the first product. The second product is that they also sell you, if you want, some implementation, some core implementation. Maybe you have heard about Cortex A72. Okay, this is the implementation of one core that ARM is giving to you and say, okay, if you have to build your own phone, take the Cortex, this Cortex, and you put it in the silicon, and that's done. The last step that I'm saying is usually 50 billion higher, so it's not really easy to do. But yeah, ARM, it gives you this the implementation, okay? It's flexible, yes, because you can take the instruction set and do your own implementation, but still you have to pay. So, and if tomorrow ARM shut down their development of their software, you don't have support anymore for your instruction set. When I say stop the software, I mean that if ARM tomorrow stops to develop the compiler, you don't have binary anymore for your chip. So you understand the impact, right? Okay, good. You can go back to sleep. And then RISC-V. RISC-V, the idea is that you have the ISA that is completely free. You set a standard for the ISA, and you build on top of that. And the compiler, it should not be something that is dependent on the company that is pushing the technology. Okay, I start using. Yes, tell me.
You said that if ARM shut down, you don't have this small binaries tomorrow, but isn't like GCC or LLVM supporting ARM?
That's true. But sometimes there are features that are not supported in the open source. So the typical situation that we had in the, for example, the number 2 now in the top 500 is the Fugaku supercomputer, right? If you run on the Fugaku supercomputer, you log in and you have at least 3 compilers. The LLVM, the GCC, and the proprietary by Fujitsu. Okay. In the proprietary by Fujitsu, that is the company that implemented the ARM instruction set, you have support for prefetch instruction, for example, that you don't have in the other 2. So it's true, I wasn't precise when I said you cannot run your binary. You can run your binary, but it's, say, suboptimal, what you can get, okay? Good observation, thank you. So the other question also, I'm now moving more like preaching for RISC-V. So if you have controversial question, you can shoot at me, and I can also admit that this is just a way to justify yet another funny game that is RISC-V, okay? So no problem in that. But I hope I gave to you at least from the non-technological point of view why RISC-V is important, okay? Good. So here you have the RISC-V ecosystem. We have to be careful with this free open source stuff, you know, because we all are we think we are very smart, so we say, okay, RISC-V is open, I'll take it, I add my 5 instruction, and now is my RISC-V, right? Is what happened with Linux at some point. You have 10 different distributions, 1,000 different distributions, and so there is a RISC-V international consortium that controls, okay, that is in charge of, say, try to keep this under some, so in order not to diverge. And then we have the hardware providers that are, here there are open source core, commercial core provider, in-house cores, and silicon providers. Okay, so here you have examples of Seagate did some microcontroller for their hard drives. We have several examples. I think there was at some point Google putting some, I think it was one of the first incarnation of the RISC-V, that the first Ariane, I think, ended up in some Google collaboration. So maybe you work at ATH and you know better this story. So, and then we have the software part. So we have a full community pushing the compiler and all the libraries that are needed in order to use this. So the ecosystem is sort of ready. So, I mean, depends. Of course, if you come with a code that has 1,000 dependencies, it's way possible that we don't have the things ready, right? We have to recompile and these kind of things. But there are things that allow you to work. Here I have a slide that, so I already used this example before, and I wanted I apologize. So it's not like Linux for software, okay? So you hear about this, a lot of people tell you, yes, RISC-V is like Linux, but for hardware, right? No. And the answer, the explanation for this is easy and is here. So when you develop software, so Linus Torvald does his own beautiful kernel, he compiles it, and he used it. Total amount of this process, it can take a lot of effort, of human effort, right? But the total amount of this is €0, okay? In the hardware step, you can develop your own RISC-V, then you can do you can develop your own architecture, you can do your nice implementation in the Blackboard, you can write your own RTL, you can have everything ready, but then you have to do a tape out, that means printing a chip. That costs a lot of money, okay? So they are not the same. They are definitely not the same, okay? So this breaks everything. Okay, I clarified this. Too much coffee, right? So I have to slow down. Okay, so I'll stop this. Here you have the link to a presentation of the creator of the Professor Razanovich of Berkeley. that explains way better what I explained so far. So this is an invited talk at the Supercomputing Conference last year. So I give all my credits because most of the ideas that I presented so far are in that talk as well. So here as the summary. So we have a standard. The idea of RISC-V is that we have a standard for an instruction set. We try to homogenize the jungle of technology that we have today in the system on chips. And we define a business model that is more flexible. So in terms of money, it allows to have more players in the market and in principle have more profits. Okay? And the last point is that it's not dependent on market fluctuation. Like, for example, I mean, if you have a company that is sold, or if you have a war in a place in the world that is, okay, if you have bans, maybe you are not, you are young enough or not exposed to this, but I was already doing ARM at some point when the US banned the US technology to Russia. At some point there was this. And I remember that year going to the ISC conference, having the queue of Russian companies coming and saying, and your ARM technology, how is it going with HPC? Because if you have a ban from a country, you cannot buy their technology, and you need your alternative, right? And somehow the idea of Europe in these years is going a little bit in this direction of having some technological independence. Okay, so these are the 4 ideas that I wanted to. Okay, how different is compared to other ISAs? So let's get a little bit more technical here. Questions before going? No, good. Stop me if you want, no worries. Well, here now I have to start selling things that are a little bit. All this is in a book that is actually in the Google Classroom that I shared. So now I tell you a thing that later we will see that is not as strong as I'm presenting it here. Okay. So the number of instruction of x86, so the Intel instruction set over the years. This is the evolution, okay? It started with 80 instruction, and it has been growing and growing and growing. So here we stop at 2014, but then we had this vector instruction and so on. So the idea behind this plot is that RISC-V is made as a very simple instruction set with very few instructions. And it can grow, but it does not need to grow like an incremental instruction set. But it can grow as a modular instruction set. What does it mean? That you can take the basic instruction set and add extensions. So here you have the list of extensions. You can take it, I mean, offline you can read it, right? So I give you the example of the vector extension. That is what we are going to see tomorrow, right? Vector extension is somewhere here. Standard extension for vector. This is old. Now is ratified at the version 1.0. 0.7 it was a couple of years ago. And it includes 186 instructions. Okay, so you can take the base instruction and add these 186 instructions, put it together, and do your own implementation. That chip is a chip that supports the basic of RISC-V. So in principle can run any binary that is compliant with the RISC-V base definition. And it has the support for an extension. Okay? So in principle we have these 2 concepts. One that is incremental ISA. So every time that you buy a new chip, you add new instruction, and your instruction set is getting fatter and fatter and fatter. And you have this modular approach in which you can add or not extension to your base. Yes, destroy me, because I know that it's not true. Okay.
No, I was curious about the modularity means that we can combine things.
Yes.
Can we combine just the base with everything? We must, I don't know, are there any rules for the combination of the modularity? There
is some constraints. Actually, the page from which I took this screenshot that I hope is this one. In the very bottom, you have examples of how you have to combine this in order to get functional things. Okay? So you cannot put everything with everything. It's like doing some recipe in the kitchen, so you cannot, I mean, no, it's not a good example, right? Because here, depending where you are in the world, you can combine things. Anyhow, yes, please.
I'm struggling a bit to see the advantage of the modular versus the incremental, because I think like one of the great challenges in developing ASA is like you need to think backward, otherwise you force people to buy new hardware and make new software.
Yes.
But here I see both for the hardware vendors, you still develop your SI or new model based also in the backward because you still need to maintain the compatibility again.
Yes.
So what exactly is the benefit of that modular?
The benefit is that if today I start my business in IoT and I want a really small microcontroller, I can base my microcontroller on the basic of RISC-V, and I have a very small piece of, say, ISA with compiler and so on. And that things will last for, say, let me say 4 years, because that's the basic. And if somebody comes and does high performance computing chip like we are doing with the vector extension with a lot of silicon area and so on, I am not forced to adopt anything of that technology in my IoT device. While if I'm doing this with Intel, I can do my IoT things tomorrow, but if in 2 years from now Intel added the vector extension to that IoT device, I have to put it in my system and I have to support it. So it makes the things, it makes the line of development, say, more independent among them. But I completely agree with all of you if this is, you see this as a shake point, because, for example, another criticism that you could have is that this is a history of more than 20 years. RISC-V is a history of a couple of years, right? So who knows how many of these extensions we will have in 5 years from now, right? If this becomes a jungle, then, okay, we are not incremental, we are modular, but if your modules are a jungle, you are not making my life easier, right? So it goes a little bit in your direction, right? So is a weak selling point, okay? I just want to show a little bit what's the rationale or the hope behind of the people that created this, and also the people that are pushing this into the market. Okay. Yes, I like raising hands. I see at least 3. Go on.
Isn't that also a problem when you talk about system on chips? You said that it was nice because you could, well, it was not nice because you had like
the fragmentation. Yes.
It made your life harder. But if the basic instruction set will be a few instructions, and every single RISC-V chip is going to implement like 10 modules of it as well, and it's not the same, then 2 chips on the same system on chip is not really compatible anymore.
Yes, but this, you are totally right, but this is supposed to be taken into account by this first layer here. So there is the RISC-V international standard. They are gathering 2 times a year. They do have the technical working group that are controlling this. And this is supposed to be, say, under the smart minds of the people that are there, not to be, say, not to diverge. So it's on us if you want, but yes, it's definitely possible. Yes, I see there.
Perhaps a similar question. If I'm a software packager, for instance,
yes.
For what instruction set to a package, for RISC-V base, or with what kind of extension? I imagine that most, like if RISC-V breaks into the desktop, right? I imagine that most would have vector extensions, right? Because we depend on them for performance systems. So if I package my software with the vector extension in mind, can people without vector extensions run it though, right? Or can they?
Yes. For this, I have an example that is already working in our lab. So in the same lab, we do have a RISC-V scalar CPU that you can buy, and a RISC-V vector CPU. So you can use your compiler to generate a scalar binary that works in the first system, and you can take the same binary, put it on the second system. Of course it works, it does not take advantage of the vector extension. The opposite is not true. If you generate a binary with vector instruction, of course if you run it on a CPU that has no vector support, the first time that the vector instruction appears, you get an illegal instruction. Okay, so this is, but say this is true with everything, even with ARM and so on. So in this sense, I would say that there is not much a problem, but not much a progress compared to what we have today. Okay, so software development is, say, more or less on the same page. If you have a compiler that supports both vector and no vector, you just switch it on and off, recompile, and it should work. Yes? Yes, please.
One of the driving forces to have a new architecture besides the complex instruction set of Intel was to have reduced the instruction set. So because this was simpler, faster, and everything else, and from there on they built the MIPS and the RISC.
Yes.
I hear from you the RISC-V, the advantage is to be independent, to be flexible, but is there also a kind of driving force which relates to the performance and to the creativity or to the need for a new architecture based on the fact that the old architectures are not good enough?
Yes.
Compared to the same development from CISC to RISC?
Yes. The answer is yes. I don't have the answer in the slide of today, but I think tomorrow when we will focus the scope to the vector instruction, I hope I can give you the example of something that is strongly oriented to the high performance computing, or at least strongly oriented to performance. And so I hope I can give the answer with examples to what you are asking today. So this is too high level. So it's not, say, community oriented. Tomorrow I really hope to get into the community. Yes, please.
RISC-V always advocate for like a simpler ISA, but when you add more and more like extensions, it will become like more complex. So how do you think that it has like using the because RISC-V should be simple. I mean, the main motive is to have a simple ISA. So don't you think we can move more to get high performance in terms of like computers? So you increase or you optimize the processor instead of optimizing the ISA.
So I'm not sure I understand your question. Is it more like, so are you asking between the difference between the instruction set and the implementation underneath?
So no, I'm just asking like when you add more and more extensions, the RISC-V ISA becomes more complex because you add more things.
That's true.
But the RISC-V advocates for simple ISA. The main motive was to have.
Okay, but then your question is more like the first one, and the answer is, once again, we have to trust ourselves. So the standard is just a human thing. We define it ourselves, okay? So there is a community that is RISC-V International, and if you go to the website, you will see a lot of logos of companies that are there, and they are the one controlling that this explosion of complexity does not happen. It can happen, yes. But in principle, we do have, say, entity that is taking care of say, not this not to diverge. But yeah, in principle, it can happen. It can even be worse than that, because if today we decide that we will add a beautiful instruction to our RISC-V and we do the summer school instruction set based on RISC-V, we can do it, and we screw it, right? Because it's not RISC-V standard compliant, because we did our own instruction set that is not supported. So, and if everybody does this, every summer school does this, in a couple of years we have a jungle of RISC-V summer school implementation, okay? So yeah, that's definitely possible, but in principle it's controlled by this. And so far it worked. So it's 9 years now, and this is working. And please also note that, note that you have extensions that are a few instructions. Okay, so we are not talking about, so I did the example of the vector, and I think the vector is the biggest one. So the one that adds more, say, complexity. So yeah, all the observation that you are doing are correct, and we have all these risks that this can explode. Yes, totally. More questions? Yes.
More like questions like a comment. Like, do you think like they should also try to partition vector extension? Because when I see this, I see like the big elephant there that is 186. And then my question goes like, if I want the integer extension, the base extension for the scalar, why do I want the floating point extension for the vector machine? Then that would be like one of my things. Like, don't you think that they also should partition that part?
The vector community agrees with you. It's like the people are already publishing little working papers saying, like, yeah, we should break this apart. So that's happening.
Yeah. It's true. I mean, whenever we start opening up this, everybody has his own preference, right? Because for us, for example, in high-performance computing, maybe we just want floating points, very good implementation of floating points, and maybe 64-bit, 32, 16. If you are fancy, you want the 8-bit floating point, and that's it. But then you have somebody that maybe want to put that into an embedded system, and you start needing other things. So yeah, I mean, for example, for the vector, as you said, there is this discussion of breaking it up and make it n parts and simpler parts that you can integrate or not. Yeah, please.
I just want to make sure, how does this extension happen? What literally here means to extend it? It's like you go and buy a new chip, what kind of comparability you have there to call it extension?
Be careful, the extension is just in the instruction set. So what we define with the new, okay, I hope it was the battery. No, when you define a new extension, you just introduce new instructions, then you have to do the implementation and the chip, okay? So in the case of the vector, for example, that is the one in which we have experience, we introduce the vector extension, we build our own chip, and you log in on our system, you compile your own source code with our compiler that support our instruction set, and you take advantage of that hardware feature. So this is a little bit what is happening today. I'm not saying this is the good way of proceeding. Probably the good way of proceeding is that we push our compiler to the community so that everybody has the support and so on. A really important point here is that if we do this, the process that I just saying, right, I do the implementation of a core supporting the vector extension. One important point is that I do not have the obligation to release as open source the implementation of my CPU with the vector support. So I can still do business with that. Okay, this is one thing that was mentioned before. Okay, so modular, not really strong. I mean, this is getting weaker and weaker, so anyhow. This is the code size, okay? So in the book, you can find the comparison between different RISC-V implementation with ARM and x86, and you see that the binary is always more or less smaller. Performance, the same thing. If you do the typical number of instruction multiply for CPI, multiply for the clock duration, you get the execution time of your application. So in the book you can find an example of comparing the Cortex A9 with the Boom RISC-V implementation, and you see that with the CoreMark, that is a benchmark that they selected very well in order to show that RISC-V was better. Anyhow, this is a little bit of a selling point, right? Yes.
Like this performance is just really coming because you have like a reduced instruction set architecture.
most probably.
But Bleacher was based on some sources, like even x86 doesn't really do CISC when you are at the code stage. Basically, you have one layer that moves the instructions to RISC before you actually start the computation. That is not actually CISC completely. Then, if you're just coming from reducing that, so how do you?
Okay, what you are saying, performance things, but maybe it get worse in the silicon area, right? Because what you are saying of this meta instruction or how is it?
So basically, converting CISC to RISC before you go to
Exactly. So that process requires some hardware support. So maybe what you are saying is say, providing same level of performance, but it adds some complexity in the silicon. So in the end, whenever you have the area of your silicon, you have to do that. You pay a little bit more because of that complexity. Yeah, I mean, these are moving things around. Usually here, the principle is that if you can do something in software instead of in hardware, try to do it in software. So that because it's cheaper, okay? But that's also another thing that you can kill me because it's not 100% sure. It's just a guideline, okay? So let's move on. This is even weaker, the documentation size, of course, if you have 30 years of documentation. But yeah, I mean, it's nice to see. If you have to start tomorrow, you can really start reading the 5 pages. I don't remember. It's really small. It's something that you can start doing and do your own implementation. I'm not surprised if you say that in one of your courses or one of your summer project you implemented a RISC-V core because it's doable. It is doable. Be careful with the time. Oh yeah, that's the try it yourself. I wanted you to. I see that almost nobody has a laptop, but I put here the QR code for the Compiler Explorer. It's nice enough because in the same page you can put your C code here and see the different compilers in action and see which is the assembly code of the 3 instruction sets. And yeah, I mean, we can look at it. I can also switch to the other window and we can play with codes. But somehow it's nice because if you look at it like this, it looks like, with a simple example, is the very same number of instructions, and they are really very similar. So probably with this slide we can say, okay, we just wasted 1 hour, right? They are definitely the same thing. And
but the Clang one is shorter.
Yes, and you can, yes, if one of your colleagues was showing me that if I change here, you were changing this, right?
Yeah, I use Clang.
Yes, if you use Clang here, you have less instruction, and also if you use Clang and you add some vector flags here, you have some vector support there. So you can start seeing vector instruction appearing, okay? So I think this is nice if you are on the swimming pool this afternoon, just take your laptop and do some example of C code that you have there and play with this. It's nice to see how they are different, this instruction set, or how similar they are, okay? I wanted to do it now, but they asked me to finish strictly at 10:15, so I will skip this. Well, probably not nice to start with this, but okay. I just give you this slide, and then we continue maybe tomorrow, starting from here. Here we have the timeline of what I mentioned before, what we did in the. Sorry, we are entering the section of the European Processor Initiative. What is this? It's basically the attempt of Europe of having some technological independence from the hardware point of view. So probably this is some feeling that I don't know if you have it or not, but basically in Europe we do have a very strong scientific software community. Okay, so the weather forecasting community, is pushed by, we have very, very good weather forecasting simulation. We do have plasma physics. We do have lattice QCD physics. So in Europe, we do have very good, strong software communities. We do not have strong hardware providers, right? Intel is US. Japanese technology are basically built and sold only in Japan or mostly in Japan. Russian and Chinese are mostly in their communities, or in AliExpress you can buy it, but okay, it's not, so you don't probably build your own supercomputer based on AliExpress. And so Europe is since several years now is trying to have some technological independence on the hardware point of view. And they started in, this is the timeline that I was mentioning at the beginning, they started pushing ARM, okay, and they say, okay, ARM is based in, so imagine to go back to 2013, no Brexit, no ARM sold to the, so ARM was based in UK was Europe, so the European Commission say, okay, let's push a little bit this, putting money, not paying ARM, but paying the research in Europe in order to push this into, right? So this is the way in which the community grows, right? And they start doing it with a European project called Mont Blanc. And in Mont Blanc, we were doing this kind of prototype based on ARM. And well, I really like to, well, this is not readable, but I really like to think that this Fugaku #1 in the top 500, these red flags here is Fugaku #1 in the top 500. It has been a couple of, so in 2020. I like to think that we in Europe contributed a little bit to that. It's true that it's a Japanese machine, but the software stack, we were really pushing it a lot in Europe, okay? And also influence a little bit the hardware design, okay? So there is no European flag there, but there is a lot of work of Europe in that. But yeah, so this was romantic, me remembering, oh, the good old times. Anyhow, Mont Blanc, we have a series of Mont Blanc 1, 2, 3, then we changed it to 2020. And here ARM has been sold to SoftBank. So here basically you start to see the boat that is changing a little bit direction, right? So, and in EPI, the European Processor Initiative, that is where we are working now and say where I would like to walk through in the next days, we are not only pushing ARM, but also RISC-V, okay? Here is, so this is basically where Europe, with all of us, actually I can be, with all our taxes or our taxes for research are going through, okay? So you can judge yourself if it is good or not. And I think, so I have more details about how this project is organized, but I think I will start from there tomorrow because I don't have enough time. We have 1 minute if you have more questions. Otherwise, yes.
So if you go like on user documentation, you can find that some instructions as some definition like this instruction is guaranteed to complete before every load before the instruction must be counted. So do you have some periodic execution guarantees for some instructions? So basically, if you have vulnerabilities in there, sometimes you modify the ISA, it has a full control over the implementation of the ISA, so it can modify the ISA more secure. If you have RISC-V implementation, you don't have this control as a standard to stay with RISC-V.
Yes.
So do you have some insight about security application in this sense? If I have an implementation which is not safe, it's not secure, I cannot modify the ISA, I guess, to make
So yeah, I get the question. We are we have the whole room that is hating us because we are getting out of time, but I can answer. First, I'm not an expert in security, I'm more in the performance. Second one, there is a working group in the RISC-V International that is dedicated to security. So I can point you to that, and they do have their own standard ratification of how to implement things. And the third thing is that in EPI, we do have a couple of partners that are working on this. One of them is the University of Pisa. So I can point you with somebody that is really expert on this. This is more like not an answer, but giving you pointers, because I don't know everything. Actually, probably you know way more than me, because if you're doing your PhD, you are in the moment in life in which you know more in your life in one topic. It will never happen again, by the way. You can be broader in your knowledge, probably, in your life. I hope so for you, but never be deeper, probably. So I acknowledge my ignorance here, but I can give you 3 pointers for you to get a little bit more.